Hello, I'm Richard Murray, a PhD student from Teen International Institute, and I'm here to tell you about some of our recent work into the back contacting of laser-induced graphene-like carbon using an all-laser approach. I know, based on the theme of the session, that we're all aware of the potential applications of low-dimensional materials. Normally this is framed in terms of what using these materials will allow us to do, for instance achieving greater sensitivity, conductivity, or even exotic behaviours. This blends well with what is being called Industry 4.0, which promises a sensor for every application and an application for every sensor. Industry 4.0 and its associated Internet of Things also boasts the term the trillion sensor economy. All in all, this speaks to a very promising future for research into this area and will allow it to mature rapidly. However, there's another way to look at Industry 4.0. The introduction of additional sensors into everyday items, especially inherently disposable ones used in packaging, presents a twofold environmental risk. Firstly, there's the obvious and shocking increased waste, but there's also the more insidious energy cost of the extraction and purification of the precursors required, and the similarly significant cost of device fabrication. With all the benefits and momentum of the Internet of Things, weighed against the very real environmental factors, we are at an impasse. Intuitively, there's a boundary where end-of-life electronics shouldn't just be thrown away, but should be part of a circular economy, or if to be disposed of, should be made of abundant materials that break down safely with a low lifetime energy cost. Innately, we all draw a line in our mind for what devices merit recycling. You wouldn't throw a smartphone into a field and expect it to break down over time. This is evidenced by the abundance of charities that collect them, the prevalence of second-hand phones, and the drawer that exists in most of our homes that have old phones and chargers, just in case. But we don't hold the same care and respect for the likes of RFID security tags, which individually have a lower energy cost than a phone, but are immediately discarded after use. This split in our behaviour shows a dark potential for the Internet of Things, especially as the number of sensors continues to increase. Dispassionately viewing this as an optimization problem, the ideal device has a low initial environmental cost, uses a minimal amount of low earth abundant material, and has a long functional lifetime, which at the end of life can either be recycled to recover the raw material, or has a low mass loading of that material, which is suitable for biodegradation. Key among these mitigations is the use of metal interconnects, which, although largely necessary, aren't easily extracted from the end-of-life device, so instead need to be mitigated. One such pathway is the subject of this presentation, laser-induced graphene-like carbon. If laser-induced graphene is going to be used to replace or supplement metallic interconnects, we need to quickly discuss what it is. In brief, as you've likely seen a couple of presentations on it already, laser-induced graphene, or LIG, is a graphene-like carbon material that is produced by the direct lasing of suitable substrates. It was first discovered by Tor et al. In 2014 while they were trying to laser-reduce graphene oxides supported by polyamide tape, or Kapton tape as it's also known, but they misaligned their system and accidentally wrote on the supporting tape, producing what we now call LIG. Since then, the number of potential substrates have been expanded to include other high glass transition temperature polymers and biomaterials like lignin and chitosan. Structurally, LIG is comprised of numerous graphene sheetlets formed by the evolution of small molecules from the precursor and the healing of the carbon scaffold. The net result is a conductive network of graphene-like sheetlets with edge defect sites and functional groups present, the quality of which is determined by the substrate and laser combination used and the formation conditions. Although the inherent disorder results in an attenuation of the electrical properties, sheet resistances as low as 10 ohms per square have been reported, which is impressive for a high surface area material that can be formed in situ without any metallic components. Further, the enhanced surface area combined with the functional groups position laser-induced graphene ideally for use in sensing applications. Having successfully been used in both electrochemical and volatile organic compound sensing, this sets out a key use case: systems where the access resistance needs to be low enough to not hamper device operation, but is not itself a critical aspect. However, until now, laser-induced graphene has normally been contacted using silver paint, as the material itself is too brittle to mechanically clamp. This method is not scalable due to the high cost of silver paint, which can also introduce contaminants into the active region. The work I'm presenting here today is a first step towards lower impact devices. A thin metallic film acts as a back contact for the LIG achieved by an all-laser process. This avoids the need for additional modification of the surface material with silver paint, or the mechanical damage of the surface of mechanical contact. For this initial demonstration, we followed traditional silicon fab processes to control the thickness of our polyamide film. The use of a wafer is not fundamental to the process we demonstrate, but instead allowed us to control our polyamide thickness and formulation. Two subsequent layers of polyamide precursor were cast and cured to achieve a suitable layer thickness of 17 micron. The laser process is then a two-step self-aligned process where the first is at high laser power and low scan speed used to ablate the polyamide in the film, and the second right then converts the top surface polyamide into high quality LIG while converting the sidewalls and remaining base material towards high quality laser induced graphene. The result is a continuous pathway from the top surface LIG to the underlying metal, mediated through the contacting structure, which we call a contact plug. The schematic I've shown is a good approximation of the resulting material. Optical images show that the initial contact plug is a keyhole shape. This is due to an operational limitation of our laser system running 2 pixels for the given region. The wall also isn't vertical, instead the material that survived the initial thinning mushrooms out. Panel G shows a higher magnification image of the region between the 2 beam pulse sensors, showing a thin film-like pattern. Fluorescent imaging in panel I indicates that this region is polyamide, suggesting that the base metal has not been fully exposed. Considering the scanning electron micrographs, we can confirm what we've already seen from the white light and fluorescent light images. There is a top surface laser-induced graphene material that is connected through a wall region to the base metal. This base is also covered in an organic material layer. The nature of these 3 regions is investigated through Raman spectroscopy. The different regions are colored accordingly, and characteristic Raman spectra from those regions are shown. The top surface is high quality laser-induced graphene, defined by its sharp 2D peak and low intensity D peak. The wall region has a more intense D peak than the top surface leg. However, the base of the plug displays more defective material, demonstrated by the convolution of the D and G peaks in addition to the broadening and attenuation of the 2D peak. Considering this alongside the fluorescence and electron micrographs, a more complete picture of the continuous LIG contact from the top surface down through the wall to a base beneath which there is a metallic layer is established. Electrical characterization of this contacting stack was carried out through a modified transfer line measurement, whereby resistance measurements are taken at each of several points at known separations along a well-defined channel width. In structures without a contacting plug, the top surface is electrically isolated from the base by the insulating residual polyamide. Therefore, we can measure the resistance through a given length of laser-induced graphene when both the probe needles are on the top surface, which we denote as top contacted. And when one is placed on the base metal and one on the top surface, we call this bottom contacted. Due to their identical formation conditions, the resistivity of the leg is the same in both contact structures, as demonstrated by their identical slopes. Due to their common laser conditions and layer structure, their sheet resistances and consequently their slopes are the same. Where they differ is in the contact resistances, which is extracted from the intercept regions of these plots. However, the distinction between the top and bottom contact structures is the access resistance associated with the contact plug, which we can estimate from the intercept. On the left we see that for a single contacting plug, the resistance is higher than if the structure was top contacted. On the right we show that using just 4 parallel contact plugs, the access resistance becomes comparable to that of a top contact. The plug access resistance can then be estimated for both the top and bottom contacted structures without the need for patterning the base metal. It is worth noting that while these values are large relative to what would be needed for energy storage, they are comparable to the sheet resistance of laser-induced graphene, making them suitable for sensing applications. The geometry of the contact isn't obvious. We know from the continuity between the top surface and the base metal they must connect, and that having more contact plugs decreases the resistance, but it isn't clear how to best scale this contact method. By varying the contact width, the dimension perpendicular to the direction of conduction, we can gain some insight. If it is a classical area contact, we would expect the resistance to decrease as 1 over the width. However, when we construct a series of different contact widths and calculate their contact resistances, they instead decrease linearly with the contact width, indicating perimeter scaling instead. Therefore, in using this method of contact, numerous small contacts should be preferred in preference to fewer large contacts. The remaining polyamide thickness beneath the top surface of the leg was estimated by producing a series of square structures to act as parallel plate capacitors with the base metal structure. Knowing the dielectric constant of polyamide, the remaining polyamide thickness is approximately 7 micron, with 10 micron of polyamide having either been converted or ablated during the conversion process. Our initial screening work agrees with this evaluation, whereby we use a single layer of polyamide approximately 8 micron thick, but requiring higher laser powers than expected to convert the polyamide, producing a highly resistant material with poor Raman characteristics. We ascribe this thickness dependence in part to the photothermal nature of the laser-induced graphene formation, whereby the thermally insulating polyamide is rapidly heated by a laser source, and a short-lived localized plasma is formed resulting in the evolution of small molecules and the healing of the carbon backbone towards a graphene-like material. If the polyamide is too thin, then the heat can escape to the support, preventing efficient conversion to a graphene-like material. So, beyond being a convenient method of self-insulating the top conductive layer from the back contact, it is also a mechanistic requirement to produce high-quality material. To demonstrate the necessity of reliable, controlled contacts near to the active region, we carried out a demonstrative cyclic voltammograms using the well-established ferro-ferricyanide reference reaction. For those unfamiliar, the key feature to look out for is the separation between the oxidation and reduction peaks, called delta EP, and the intensity of the peak above the background. These features can be used to determine how far a system deviates from ideality. We want to see highly intense signals with spacings of approximately 56 millivolts. Returning to the impact of contact resistance level voltammograms, we see here that the exposed gold plot has a separation of 69 millivolts, close to the ideal value. We also show two uses of the contact plugs, one within the O-ring defining the active electrochemical area, and the other external to it. The internal plugs have a lower separation, but lower signal intensity, while the external plugs have a higher signal but a larger separation. The peak separation decreases with the decreasing axis resistance, reducing the overpotential required to achieve the redox process, while the attenuated signal indicates that the inclusion of the contact plugs in the active area reduces the area available to carry out the redox process. To investigate the trade-off between area consumed by the plugs in the active area and the impact of axis resistance by entry track length, cyclic voltammograms were carried out at known distances from the contact plugs. The peak separation increased linearly with the increased axis resistance. Also evident is the diminishing signal to background with increasing distance. Therefore, if an externally contacted strategy is required, the track should be minimized, if possible, to ensure high-quality electrochemical sensors. Similarly, we vary the number of plugs present within the same footprint of laser-induced graphene material. There is a marked decrease in the peak separation from one plug to 4, after which an additional plug only serves to reduce the active area of the electrode. This suggests that reducing the contact resistance is necessary to achieve high-quality results, but this contact resistance need only be low relative to the sheet resistance of the laser-induced graphene. Finally, when the electrochemical kinetics are extracted from the peak separation and intensity for a number of scan rates, we see that the system with the lowest axis resistance, the internally contacted structure with 4 plugs, demonstrates kinetics competitive with exposed gold of a similar footprint area. This demonstrates the potential for the innate high surface area of LIG if the axis resistance challenges are surmounted. Today I showed you our latest work on back contacting polyamide laser-induced graphene using a silicon wafer as a carrier. This allowed us to try different thicknesses of film to ensure we could produce high quality material while still achieving our contact. But the high cost wafer and processing conditions of the fab aren't necessary. Metal coated polyamide films are already available commercially and provide a rich opportunity for further work and investigations. This is only a step towards a sustainable implementation of the Internet of Things. This is a pathway to reduce the amount of high energy material consumed in the fabrication of devices intended to be disposed. We have done this by using polyamide, a synthetic polymer that won't biodegrade. While this is an improvement over intensive use of semiconductors and metals, it poses its own challenge. An answer to this next step is also possible through the production of laser-induced graphene-like carbon from biomaterials and biopolymers such as cork and chitosan, which have already been successfully converted to laser-induced graphene. We have demonstrated a novel, two-step method of back-contacting laser-induced graphene. This all-laser method allows for the direct formation of LIG-based devices without the need for additional modification or the use of expensive unscalable materials like silver paint. This provides a facile additive manufacturing stepping stone towards a more sustainable Internet of Things. Thank you for your attention. I would like to take this opportunity to thank my funding agencies for the ability to carry out this work, my colleagues for their help and advice, and especially my supervisors Aidan and Daniela. If there's time, I'd like to answer any questions, and